Hopefully you've taken some time to think about these rules of integration a little bit, because I'm going to go one by one, just kind of explaining them in the context of this area diagram in the hopes that we can make some sense of what they're talking about. I would be remiss to skip over this section below the diagram but above the rules, because it is kind of helpful to remind us of something that we talked about in I think the last day before we departed from online or in-person classes, and that's the idea of direction. Direction matters when we're talking about these area problems, because in calculus terms, it is possible to have a negative area. When we think about the geometry we learned in 8th or 9th grade, it probably didn't even seem possible, let alone realistic, to have a negative area of something. But because our areas are going to be overlaid on a coordinate plane, where x and y actually mean positive or negative numbers on the axes, the context there means that negative numbers exist, and it is possible to have a negative area. For example, one such negative interpretation would be if you had an integral, and you can just think of this symbolically for now. If you had an integral from b to a of this region that we'll call f of x dx. So remember, symbolically, the sum of all of the individual little dots or rectangles that you can possibly think about in this shaded region are all going to have bases of dx and heights of f of x. Remember, base times height is an area, and this integral refers to the sum of all of the areas from b to a. Remember, the lower limit of an integral tells you where the area starts, and the upper limit tells you where the area ends. So if you think about this for a moment, think about the implications of those rectangles. If dx is the base and f of x is the height, think about those things. Dx is going to be measuring to the left. Dx would be taking us from b towards a, to the left. The height would be going up. So every rectangle I draw, no matter how big or how small, is going to have a negative base, because the base is going to be pointing to the left, and a positive height, because the height's going to be pointing up, and negative times positive, base times height, would give me a negative result. So the area of my first rectangle, no matter how big it is going to be a negative area. And then my next rectangle is also going to have a negative area, because it too is going to be going towards the left and up. Negative times positive is negative again. And if I have a negative area and a negative area and a negative area and a negative area and a negative area, no matter how many negative areas I add up, the total is going to be one gigantic negative value. In other words, one gigantic negative area. So all that to say, direction matters. If the base is referring to a negative direction, but the height is referring to a positive direction, then the overall answer is going to be a negative answer. The overall integral, or area, will be a negative value. Now, that's kind of summarized here in these little bullet points, so to speak. If a is less than b, the integral is being analyzed from left to right, so dx is positive. If a is greater than b, that's basically just saying pay attention to direction. There's really no need to formalize this in any specific way. Just make sure that you're thinking about the idea of paying attention to the direction. Now, on to the rules. The first rule, as I alluded to in the previous video, refers to the integral from a to a. Remember, I'm purposely pronouncing it that way, from a to a, as a start-stop implication. If I'm looking at a geometric shape beginning at a and ending at a, I really don't have anywhere to go. If I start at a and end at a, there's literally no base to this rectangle. And if I think about that in area terms, remember everything is going to be an area, I would have a base times a height, of course, but the base would be 0. Like, there's literally no horizontal distance I can possibly go. The height is going to be whatever it's going to be, but I don't care what it's going to be, because 0 times whatever that height is just going to be 0. So the area of a region that has literally no base, that doesn't go anywhere, is always going to be 0. And that's what rule number 1 essentially says, that the area from A to A is impossible to calculate because it has a base of 0, so the overall answer is always going to be 0. Now, I'm not going to take the time to write these things only because I'm really slow at writing and talking simultaneously. So my suggestion is, if you can, transcribe these rules either in my words or in your own words, and pause, rewind, fast forward, do whatever you need to do to kind of make sure you get the verbiage as I'm talking through these things. If you want to see my answers written out, you can always open the answer key, because I have written out the answers in a slightly more stylized version. And if it helps you to see my answers in addition to hear them, I would have that tab open somewhere on a device, or at least refer to it at some point while you're writing your own answers so that you have it. Now, on to the next rule. Again, apologies I'm not writing these down, but hopefully in me covering them verbally, you'll be able to see what I'm talking about using the diagram and write it in your own words to process it. In the second rule, we're talking about the area from b to a of f of x dx. And we're claiming that that is equal to the negative from a to b. And that might seem symbolically a little bit complicated, but that kind of alludes to something we were just talking about. Remember how we just said that the area from b to a would have a negative base, starting at b going towards a? When you think about it, no matter what, whether I go from a to b or b to a, the physical size of this region is going to be the same no matter what. If I think of this region as a weird, like, trapezoidy thing, or a bunch of rectangles added up, whatever, if I calculate from b to a, I'm going to have a negative base, positive height, all of this stuff is going to add up, and it's going to give me an answer that is definitely going to be negative. But if I went from a to b, the value of the base would still be the same. Yeah, it'd be positive this time, but it'd be the same number. The height would be the same number. So arguably, I'd get the same answer if I was going from a to b. It would just be a positive if I was going to the right and a negative if I was going to the left. The physical size of the region would be exactly the same, because the length of the base and the length of the height would be the same no matter which direction I'm going. The only thing that's affected by the direction is the sign of the number. So that's what rule number 2 is basically saying, that if you go in one direction, say backwards, that's just the negative of going the other direction. That it's the same literal number, just negative if you're going backwards. That's all that rule is saying. Rule number 3 is kind of an interesting one. And for rule number 3, I'm actually not going to refer to the diagram on this page because I think it might be a little bit abstract. Instead, I'm going to go with something a bit more concrete. So if you want to draw this for yourself, you're welcome to do so. If you want to just follow along with what I'm doing and just watch as I'm doing it, that's fine too. I don't think this is a mandatory thing. But I think rule 3 is a little bit more easily understood if you have something that you can kind of latch onto. So I made up a function for f of x, but I purposely picked a really nice recognizable function. I picked something like 2x. Because we know 2x, that's an easy function. We can picture what its graph looks like. We can easily do calculus with it. So I tried to pick something really friendly. I also set an interval. So instead of referring to this sort of abstract a to b, I picked an actual interval from 1 to 3. So that way we have a distinct start and end point we can focus on. So picture what that region would look like. I took the opportunity to graph the equation 2x, and I took the opportunity to kind of delineate a little bit what that region from 1 to 3 would look like. So I'm referring here to this little shaded space that looks kind of trapezoidish, which is great, but it doesn't really matter right now. What I want us to think about instead is the rule that we're trying to explore. The rule says, well, what if you have this extra constant k? Now remember, the beauty of implicit notation is I can tell k is supposed to be a constant, because f of x dx, that dx implies that everything was in terms of x, remember implicit? So k, a totally different letter, must be some sort of constant, because the only variable I'm allowed in this problem is x, according to my implicit notation. So the supposition here is that the k, if you have a k or a constant multiplying a function, could be brought outside of an integral, and that's like the same thing. That if you have a constant, you can essentially move it to the outside of an integral, and that would be completely fine. You might be thinking, well, why do I need to do that? And I'll show you eventually why that comes in handy, but for now, let's just make sure we understand why we're actually allowed to just move things around like that. Because that almost seems a bit cavalier, like really? I could just pluck a number straight from inside of the problem and stick it outside the problem. That seems a bit flexible, and we know that math doesn't usually just let you move things around willy-nilly. So let's dig a little bit deeper as to why that would work using this example. Essentially, what we're trying to prove right now is that if I had a k, and I purposely picked a k value that was kind of nice, so there's my k value of 4. We're going to compare what it would be like if I had the 4 inside of the integral versus pulling the 4 outside of the integral. Now, this is something that you can do both algebraically with calculus, an antiderivative, and geometrically by finding an area. So I'm going to show it with the area approach, but if you want to do this also with calculus, you are certainly welcome to do so, and you can prove to yourself that it actually works both ways. But I'm going to show the algebra here just so you can connect it again to this whole geometry area connection thing. If we think about this logically, 4 times f of x dx kind of goes back to what we were saying about base times height. Remember how we were saying that dx is kind of like the base of something and f of x is kind of like the height of something? Let's say for a moment that that 4 really is going to make an implication on the height of our potential shape. That if I want to take this shape and make all the heights 4 times bigger, we're really going to have to transform our shape. So I'm going to do a quick redrawing for a second, and I'm going to see what would happen there. If I do want to make this shape 4 times bigger, what would that do? So if I start to kind of make a hypothesis, let's just think. My shape at x coordinate 1 is currently 1, 2 tall. So if this is claiming that I'm going to make the height 4 times taller, it's currently a height of 2. 4 times taller means now I'm going to have a height of 8. Obviously not drawn to scale. Sorry. Now what about the height on the other end? The current height is 6, so I'll label that here. And if at this x coordinate I want to make it 4 times taller, 4 times 6 would give me a new height of 24. Again, not drawn to scale. Apologies. So, let's think about the shape. The horizontal distance between 1 and 3 hasn't changed, so that, in terms of my area, is still going to be consistent, but now I have a completely new physically sized shape. Let's think on this for a moment. Previously, I had a bit of a trapezoid. So if I think about the formula for a trapezoid, the formula for a trapezoid is 1/2 base 1 plus base 2, 2 plus 6 would be 8, times the height, which is 1, 2, and 1/2 times 8 times 2 is half of 16, which is 8. Okay, so the original shape had an area of 8. Now let's think about my new transformed shape. My new transformed shape was a new trapezoid, but still a trapezoid. So 1/2 times base plus base, 8 plus 24 is 32, times the height of the trapezoid, 1, 2. Half and 2 are going to cancel each other out, which gives me a total area of 32. Now, did you notice something? 8 and 32. They do have a relationship there. 32 is 4 times bigger than 8. So if I found the traditional area from 1 to 3 of the regular old function as is, which we know was 8, we've now found that the area 8 times 4 gives us an accurate representation that is the exact same as individually increasing each part of the shape by 4 and finding the new shape altogether. Now, the reason I purposely chose to do this in such a tedious way with this area is so you could see it really does work. And it works beautifully. The fact that it works basically reinforces to us that if you have constants, you can move them around. That's all you need to take away from this little exercise, is that if you have a constant inside of an integral, you can move the constant outside of the integral, and it doesn't change the actual value of the integral. The actual value of the integral will be exactly the same no matter what. 4 times 8 is still going to give you the same thing as the actual area of all the heights 4 times bigger. So it's interesting to think about in that way that we actually can move constants around like that, but that's what rule number 3 is essentially trying to say. That yep, you can move constants around, you can move a constant inside or outside an integral, you can basically rearrange things and clean things up in any way that's helpful, because constants are movable. Variables are not. We can't move variables outside of an integral, but constants, a-okay, fair game. Now, if you wanted to prove this to yourself algebraically, you definitely could as well, and I'll leave that as an exercise to you if you want to try to do it algebraically. And just to remind you what I mean by algebraically, if you had the integral from 1 to 3 of 4 times the f of x was 2x dx, which is obviously the integral from 1 to 3 of 8x dx, that would be the exact same as the integral from 1 to 3 of the regular old function, f of x dx, with a 4 outside. If you want to prove this to yourself by doing this as a true antiderivative, do the antiderivative of 8x and evaluate it at 1 and 3 with a little vertical bar. Same thing here, do the integral of 2x, evaluate it at 1 and 3 with a little vertical bar, and then just take the whole result and multiply times the 4 that's outside. Again, you will not be surprised to find out you will get the same answer both times. And, not surprisingly, that answer will be, spoiler, 32. So, anyway, all that to say, rule number 3 says you can move constants. If you want to summarize it in the shortest possible way, rule number 3 says you can move constants around. Now, rules 4 and 5 are kind of saying a very similar thing, so I'm going to lump rules 4 and 5 together in a sort of common sense way, and this is probably the easiest rule for most people to understand because it probably appeals to your better judgment that you've already established since your geometry classes, that if you have the integral from a to b of smaller parts, then that's the same thing as finding each smaller part and just adding them together. The plus or minus says that, yeah, if it's a negative, like if you're going backwards, you'd have to subtract them together, whatever. But that's basically all that rule 4 and rule 5 are saying. That if you wanted to take smaller pieces and add them together, that's the same thing as finding one gigantic piece. That's pretty common sense. That's like saying if I wanted to break up shapes like maybe into 3 and find this one plus this one plus this one and call it the area of the whole thing, I'm allowed to do that. That, in essence, is rule 4. Rule 4 is saying, yeah, break it up if you want. Rule 5 is saying, yep, break it up if you want. That's all it's saying. So, no big deal there. Take some time to really make sure that these rules make sense. Take some time to translate these words into your rules into your own words, and then take some time to check the answer key, process what I wrote, see if notation-wise it makes a difference to kind of take my input into account. And before you start the next video, let the ideas marinate a little bit. It's kind of a lot to think about, but hopefully you're finding that it builds on your intuition, not just a calculus intuition, but your geometry intuition and just basic number sense. And once you have those intuitive ideas fairly well established, we'll go on to page 3, which is where we're going to do a little bit more of a practical application of these rules.